Max Planck, the brilliant physicist who would later become known as the father of quantum theory, was born on April 23, 1858, in Kiel, a coastal city in northern Germany. At the time of his birth, Germany was not yet the unified nation we know today, but a collection of smaller states. Planck was born into a highly educated and respected family, which played a major role in shaping his intellectual journey. His full name was Max Carl Ernst Ludwig Planck, and he was the sixth child in his family. His father, Johann Julius Wilhelm Planck, was a professor of law and a highly respected legal scholar. His mother, Emma Patzig Planck, came from a cultured and educated background as well. Education, discipline, and intellectual curiosity were deeply valued in the Planck household, and this environment strongly influenced young Max from a very early age. Childhood and family environment. Max Planck grew up in a family that believed in knowledge, music, and discipline. His parents encouraged all their children to study seriously and develop strong moral values. The family moved several times during his childhood because of his father's academic career, but they eventually settled in Munich, which became a central place in Max Planck's early education. As a child, Max Planck was not considered a child prodigy in the way some famous scientists were, such as Albert Einstein or Isaac Newton. However, he was known for being highly intelligent, disciplined, and curious. He had a calm personality and was known for his logical thinking and strong sense of responsibility. Planck also had a deep love for music, especially the piano. He was so talented that he once considered becoming a professional musician. Music remained an important part of his life, and many historians believe that his musical training helped him develop the mathematical and logical thinking skills that later made him a great physicist. Early school education. Max Planck attended the Maximilians Gymnasium in Munich, one of the most prestigious schools in Germany at the time. The gymnasium system in Germany was known for its rigorous academic training, especially in mathematics, science, languages, and philosophy. At school, Planck showed strong abilities in mathematics, physics, and classical languages. His teachers noticed his exceptional analytical skills and his deep interest in scientific questions. He was particularly fascinated by the laws of nature and how the universe worked. One of the most important moments in his early education came when a teacher introduced him to the principle of energy conservation. This scientific idea deeply impressed Planck and inspired him to pursue physics. He later said that learning about the law of energy conservation was a turning point in his life, and it convinced him that physics was the field he wanted to dedicate his life to. Interest in science and philosophy. During his teenage years, Planck was not only interested in science, but also in philosophy. He read books about the nature of reality, truth, and knowledge. This philosophical curiosity later influenced his scientific work, especially his thoughts about the nature of physical laws and the limits of human knowledge. Planck believed that science should seek universal truths, and he was deeply influenced by the idea that the universe follows precise and beautiful mathematical laws. This belief guided his scientific career and motivated him to search for fundamental principles that govern nature. University education. After completing his secondary education, Max Planck entered the University of Munich in 1874 to study physics. At that time, physics was dominated by classical theories developed by scientists like Newton, Maxwell, and thermodynamics pioneers. Quantum theory did not exist yet, and most scientists believed that classical physics could explain all natural phenomena. At the University of Munich, Planck studied under some of the greatest scientists of his time. He attended lectures by Philip von Jolly, a professor of physics who once advised Planck that physics was almost complete and that there were no major discoveries left to be made. This statement later became famous because Planck himself would prove it completely wrong by discovering quantum theory. Despite this discouraging advice, Planck remained passionate about physics. He believed that even if most laws were known, there were still deep mysteries waiting to be solved. Studies in Berlin after studying in Munich, Planck continued his education at the University of Berlin, one of the leading scientific centers in Europe. There, he studied under famous physicists such as Gustav Kirchhoff and Hermann von Helmholtz, who were pioneers in thermodynamics and electromagnetism. In Berlin, Planck developed a strong interest in thermodynamics, the study of heat and energy. He was fascinated by the laws that govern energy transformation and entropy. His doctoral research focused on the second law of thermodynamics, a topic that would later play a crucial role in his scientific breakthroughs. Doctoral degree and early academic career in 1879, Max Planck earned his Ph.D. in physics from the University of Munich with a dissertation on thermodynamics. After completing his doctorate, he began working as a university lecturer. He first worked at the University of Munich and later at the University of Kiel. Planck was known as a brilliant teacher and a highly disciplined researcher. He published several scientific papers on thermodynamics, which gained him recognition in the scientific community. His work was respected, but at this stage, he was not yet considered a revolutionary scientist. Personal character and work ethic during his early academic years, Planck developed a reputation for being extremely disciplined, patient, and honest in his scientific work. He believed that science should be based on careful experiments and logical reasoning, not speculation. He was also known for his modest personality and strong moral principles. Planck believed that scientific laws were not invented by humans but discovered, and that the universe followed objective truths that scientists must uncover. This belief later influenced his approach to quantum theory, even though his discoveries challenged classical ideas. Moved to Berlin as a professor in 1889, Max Planck was appointed as a professor of theoretical physics at the University of Berlin, one of the most prestigious positions in Germany. This appointment marked a major milestone in his career. In Berlin, he had access to the best laboratories, students, and scientific discussions. At this time, Planck was still a strong supporter of classical physics and believed deeply in deterministic laws of nature. He did not expect to revolutionize science. Instead, he aimed to refine and perfect existing theories, especially in thermodynamics and radiation theory. Early scientific reputation by the end of the 19th century, Planck had established himself as one of the leading theoretical physicists in Germany. He was respected for his deep understanding of thermodynamics and his rigorous scientific methods. However, he was still considered a traditional scientist, not a radical thinker. Ironically, it was this traditional and conservative scientific mindset that led him to discover quantum theory. While trying to solve a classical physics problem, he introduced a revolutionary idea that changed science forever. By the late 19th century, physics was considered almost a complete science. Most scientists believed that the laws discovered by Isaac Newton, James Clerk Maxwell, and others had already explained nearly everything in the universe. Classical physics described how objects move, how light travels, and how energy behaves. Many physicists thought that only small details remained to be discovered. Max Planck was one of those scientists who deeply believed in classical physics. He respected the work of Newton and Maxwell and thought that nature followed strict, predictable laws. Planck was not a revolutionary thinker at first. Instead, he was a conservative scientist who trusted traditional theories and methods. However, it was this very belief in classical physics that led him into a great scientific struggle that would change history forever. The blackbody radiation problem, one of the biggest unsolved mysteries in physics at the time, was blackbody radiation. A blackbody is an ideal object that absorbs all incoming light and re-emits energy as heat and light. Scientists studied how hot objects glow and how they emit radiation at different temperatures. Classical physics tried to explain this phenomenon using known laws. Two major theories existed: Wien's law, which worked well for high-frequency radiation, Rayleigh Jean's law, which worked well for low-frequency radiation, but there was a serious problem. When classical equations were applied to high frequencies, they predicted that a hot object should emit an infinite amount of energy. This was impossible and clearly did not match experimental results. This failure became known as the ultraviolet catastrophe. Physicists were confused and frustrated. Classical physics, which had been so successful in explaining nature, suddenly failed in this important area. Many scientists tried to solve the problem, but no one could find a complete solution. Planck's determination to solve the mystery, Max Planck, was deeply interested in thermodynamics and radiation theory. He believed that the problem of blackbody radiation could be solved using classical physics. He spent years studying experimental data and mathematical formulas to find a solution that matched reality. Planck was not trying to destroy classical physics. In fact, he wanted to save it. He believed that there must be a mathematical formula that could explain radiation without breaking known laws. For years, Planck worked in isolation, analyzing data and searching for a theory that could fit all experimental results. He tested different equations and models, but none were completely successful. A radical idea born from desperation by 1900, Planck realized that classical physics alone could not explain blackbody radiation. He was forced to consider a radical idea that went against everything he believed. He proposed that energy is not emitted continuously, but in discrete packets. These packets were later called quanta. According to Planck, energy could only be emitted or absorbed in fixed amounts, not in any arbitrary value. This idea was completely revolutionary and shocking to the scientific world. Planck himself did not fully believe this idea at first. He considered it a mathematical trick rather than a true description of nature. But the equations worked perfectly and matched experimental data exactly. Planck's constant while developing his theory, Planck introduced a new fundamental constant, now known as Planck's constant h. This constant relates the energy of a quantum to its frequency. This was one of the most important discoveries in physics. Planck's constant became a key part of quantum mechanics and is used in countless scientific calculations today. At the time, Planck did not realize how important this constant would become. He thought it was just a small part of his radiation theory. Scientific resistance and doubt when Planck published his work in 1900, many scientists were skeptical. The idea that energy comes in discrete packets contradicted classical physics, which assumed energy was continuous. Even Planck himself was hesitant to accept the full implications of his discovery. He believed that classical physics was still correct and that quantization was just a temporary solution. However, other scientists soon realized the importance of Planck's work. In 1905, Albert Einstein used Planck's quantum idea to explain the photoelectric effect, proving that light behaves like particles. This confirmed that Planck's theory was not just a mathematical trick, but a real physical phenomenon. Planck's internal conflict, Max Planck, struggled deeply with the meaning of his discovery. He was a traditional physicist who believed in determinism and classical laws. Quantum theory suggested that nature behaves in strange and probabilistic ways. Planck once said that his discovery was an act of desperation, not a planned revolution. He was trying to fix a problem in classical physics, but instead, he opened the door to a completely new world of science. He later admitted that his theory marked the beginning of a new era in physics, even though he personally preferred classical explanations. The birth of quantum physics, Planck's solution to the blackbody radiation problem, is now considered the birth of quantum physics. His struggle with classical physics led to one of the greatest scientific revolutions in history. What began as an attempt to save classical physics ended up destroying its dominance and creating a new scientific framework that changed how we understand reality. In the late 19th century, the world of physics seemed almost complete. Scientists believed that nature had already revealed most of its secrets. The laws of motion described by Isaac Newton, the theory of electromagnetism developed by James Clerk Maxwell, and the principles of thermodynamics had given scientists a powerful framework to understand the universe. Many physicists thought that only small details remained to be solved, and no major discoveries were left. Max Planck was one of these scientists. He was a devoted follower of classical physics and believed deeply in its principles. He admired the works of Newton and Maxwell and believed that the universe operated according to precise, deterministic laws. Unlike later revolutionary scientists, Planck did not begin his career as a rebel or radical thinker. Instead, he was conservative in his scientific beliefs and trusted traditional theories. However, as he continued his research, Planck encountered a mysterious problem that classical physics could not explain. This problem would challenge his beliefs, push him into intellectual conflict, and eventually lead him to one of the greatest discoveries in scientific history. The crisis in classical physics by the end of the 1800s, physics faced several unsolved problems that did not fit into the classical framework. One of the most important was the problem of blackbody radiation. Scientists were studying how hot objects emit light and energy. When an object is heated, it glows and releases electromagnetic radiation, such as visible light and infrared radiation. This behavior was called blackbody radiation. Classical physics tried to explain this phenomenon using known laws of thermodynamics and electromagnetism. Scientists developed mathematical formulas to describe how energy is emitted at different frequencies and temperatures. Two major theories emerged, Wien's law and the Rayleigh-Jeans law. Each of these laws worked well in certain ranges of frequencies, but neither could explain the full spectrum of radiation. The Rayleigh-Jeans law predicted that the energy emitted by a hot object would increase infinitely at high frequencies. This prediction was clearly wrong because experiments showed that energy actually decreases at very high frequencies. This contradiction became known as the ultraviolet catastrophe, a term that described the failure of classical physics at short wavelengths. For physicists of that era, this was a shocking problem. Classical physics had explained so many phenomena, but now it was giving absurd predictions. The scientific community was confused and searching for a solution. Planck's determination to defend classical physics, Max Planck was deeply disturbed by this problem. He believed strongly in classical physics and wanted to find a solution that would save it. He did not want to create a new theory or challenge existing laws. Instead, he believed that there must be a hidden mathematical relationship that could explain blackbody radiation within the classical framework. Planck devoted years of his life to studying thermodynamics and radiation. He analyzed experimental data from laboratories across Europe and worked tirelessly to derive an equation that matched reality. He spent countless hours performing calculations, testing hypotheses, and refining his theories. Planck believed that nature was governed by universal laws, and that these laws could be expressed mathematically. He believed that if he could find the correct equation, the mystery of radiation would be solved without breaking classical physics. The influence of thermodynamics. Planck's background in thermodynamics played a crucial role in his struggle. He was fascinated by the second law of thermodynamics, which deals with entropy and the direction of natural processes. He believed that thermodynamics held the key to understanding radiation. He studied how energy is distributed among molecules and how heat behaves in physical systems. Planck believed that radiation must follow similar principles. His deep understanding of thermodynamics allowed him to approach the radiation problem with a unique perspective. However, despite his expertise, classical thermodynamics alone could not solve the problem. Planck found himself facing a wall that classical physics could not cross. Experimental evidence against classical theory at the same time. Experimental physicists were producing precise measurements of blackbody radiation. These experiments showed that energy distribution followed a specific curve that classical theories could not reproduce. No matter how Planck adjusted the equations, classical physics failed to match the experimental data. This was a painful realization for Planck. He had built his career on classical physics, and now it was failing in one of the most fundamental areas. He began to realize that something deeper was missing from existing theories. Planck once described this period as one of intense intellectual struggle. He was torn between his loyalty to classical physics and the undeniable evidence that it was incomplete. A revolutionary idea from desperation. By 1900, Planck reached a point of desperation. He realized that classical physics could not fully explain radiation. In order to match experimental data, he introduced a bold and radical assumption. He proposed that energy is not emitted continuously, but in small, discrete packets. These packets of energy were later called quanta. According to Planck, atoms could only emit or absorb energy in fixed amounts, not in any arbitrary value. This idea was completely against classical physics, which assumed that energy could take any value. Planck himself was shocked by this assumption. He did not initially believe it represented reality. He considered it a mathematical trick that helped him fit the experimental data. But the theory worked perfectly. Planck's constant and mathematical breakthrough while developing his theory, Planck introduced a new constant into physics, now known as Planck's constant. This constant relates the energy of a quantum to its frequency and is one of the fundamental constants of nature. Planck's constant became the foundation of quantum mechanics and is used in countless scientific calculations today. It determines the scale at which quantum effects become significant and defines the relationship between energy and frequency. At the time, Planck did not realize how important this constant would become. He believed he had simply found a mathematical solution to a technical problem. Scientific reaction and skepticism. When Planck published his theory in 1900, the scientific community was skeptical. Many physicists did not accept the idea of quantized energy. It contradicted centuries of classical thinking and challenged the deterministic view of nature. Even Planck himself was hesitant to accept the full implications of his discovery. He continued to believe in classical physics and hoped that quantum theory would eventually be explained in classical terms. However, his idea soon inspired other scientists. In 1905, Albert Einstein used Planck's quantum concept to explain the photoelectric effect, proving that light behaves like particles. This confirmed that Planck's theory was not just a mathematical trick, but a real physical phenomenon. Planck's internal conflict. Max Planck struggled internally with his discovery. He was a conservative scientist who believed in deterministic laws and classical explanations. Quantum theory suggested that nature behaves in discrete steps and involves probability and uncertainty. Planck did not like the philosophical implications of quantum theory. He preferred a universe governed by precise and predictable laws. Yet, he could not deny the success of his theory and the experimental evidence supporting it. He later described his discovery as an act of desperation, not a planned revolution. He was trying to solve a classical problem, but he ended up starting a new scientific era. The end of classical dominance, Planck's struggle with classical physics, marked the beginning of the end for classical dominance in science. His theory opened the door to quantum mechanics, which would later be developed by scientists like Einstein, Bohr, Schrödinger, and Heisenberg. Quantum theory revolutionized our understanding of atoms, molecules, and the universe. It led to the development of modern technologies such as semiconductors, lasers, computers, and medical imaging. Planck's struggle showed that even the most trusted scientific theories can be incomplete, and that progress often comes from questioning established ideas. By the dawn of the 20th century, Max Planck stood at the center of a scientific storm. His attempt to solve a classical physics problem had led him to a theory that challenged centuries of scientific thinking. What began as a mathematical solution soon became the foundation of a completely new branch of science, quantum physics. At first, Planck himself did not fully understand the consequences of his discovery. He thought of quantization as a temporary tool, not a fundamental law of nature. But history would prove that his work was far more revolutionary than he ever imagined. The impact of Planck's quantum hypothesis. When Planck introduced his quantum hypothesis in 1900, it quietly entered scientific literature. At first, only a few physicists paid attention to it. Many believed it was just another mathematical trick to solve a technical problem. However, within a few years, the scientific world realized that Planck had opened a door that could never be closed. In 1905, Albert Einstein used Planck's quantum idea to explain the photoelectric effect, showing that light behaves like particles called photons. This was one of the first experimental proofs that Planck's idea was real and not just a theoretical assumption. Einstein later won the Nobel Prize for this work, not for relativity, but for confirming quantum theory. Soon after, Niels Bohr applied quantum ideas to explain the structure of atoms, proposing that electrons move in fixed energy levels. This model explained why atoms emit specific colors of light and why classical physics failed to describe atomic behavior. Other scientists, including Erwin Schrödinger, Werner Heisenberg, and Paul Dirac, expanded quantum theory into a complete framework that described the microscopic world. All of this began with Planck's struggle to solve the blackbody radiation problem. Planck's Nobel Prize and recognition in 1918, Max Planck was awarded the Nobel Prize in Physics for his discovery of energy, quanta. By this time, the scientific community fully recognized the importance of his work. His theory had transformed physics and inspired a new generation of scientists. Planck became one of the most respected scientists in the world. He served as the president of the German Physical Society and later as the president of the Kaiser Wilhelm Society, which is now known as the Max Planck Society. This organization became one of the world's leading scientific research institutions. Despite his fame, Planck remained humble and dedicated to science. He never claimed that he had intentionally created quantum theory. Instead, he often said that his discovery was forced upon him by nature. Philosophical struggles with quantum theory. Although Planck introduced quantum theory, he was never completely comfortable with its philosophical implications. Quantum mechanics suggested that nature is not fully deterministic, and that probability plays a fundamental role in physical processes. This idea troubled Planck, who believed deeply in deterministic laws and objective reality. He disagreed with some later interpretations of quantum mechanics, especially the Copenhagen interpretation, which suggested that reality is not fully defined until measured. Planck believed that physical laws exist independently of observation, and that science should describe an objective reality. This philosophical struggle shows that even the creator of quantum theory had doubts about its deeper meaning. Yet, he continued to support scientific research and encouraged younger scientists to explore the new theory. The end of the classical era, Planck's struggle with classical physics, symbolized the end of the classical era in science. For more than 200 years, Newtonian mechanics and classical electromagnetism had dominated scientific thinking. Planck's discovery showed that these theories were incomplete and that new laws were needed to describe the microscopic world. Quantum theory revealed that atoms and particles behave in ways that defy classical intuition. Energy is quantized, particles can behave like waves, and uncertainty is built into the laws of nature. These ideas changed not only physics, but also philosophy, chemistry, and technology. Planck's work marked the beginning of modern physics, along with Einstein's theory of relativity. Technological revolution inspired by Planck, the consequences of Planck's struggle are visible in modern technology. Quantum theory led to the development of semiconductors, transistors, lasers, and computers. Without quantum mechanics, smartphones, computers, GPS systems, and medical imaging technologies like MRI would not exist. Planck could never have imagined that his mathematical solution would one day power the digital world. His struggle with classical physics laid the foundation for the technological revolution of the 20th and 21st centuries. Planck as a teacher and mentor as a professor in Berlin. Planck taught many students who later became famous scientists. He encouraged young physicists to explore new ideas and supported their research. Even though he personally preferred classical physics, he understood the importance of scientific progress and open-mindedness. Planck believed that science advances through generations, and that younger scientists often bring revolutionary ideas. He once said that science progresses one funeral at a time, meaning that old ideas often disappear only when older scientists retire or pass away. Personal strength during difficult times while his scientific career flourished. Planck faced many personal tragedies. He lived through World War I and World War II, periods of great suffering in Germany. He lost his first wife, several children, and even his son, who was executed for participating in a plot against Adolf Hitler. Despite these tragedies, Planck remained dedicated to science and education. He believed that knowledge and truth were more important than political ideologies and conflicts. His moral strength and dedication made him not only a great scientist, but also a respected human being. Legacy of Max Planck. Max Planck passed away in 1947 at the age of 89. By the time of his death, quantum theory had become one of the most important branches of science. His name lives on in many scientific institutions, including the Max Planck Society, Planck units, and Planck's constant. His struggle with classical physics is remembered as one of the greatest turning points in scientific history. He did not set out to revolutionize science, but his determination to solve a problem led him to a discovery that changed our understanding of reality. The discovery of quantum theory is one of the greatest turning points in the history of science. Before the 20th century, scientists believed that classical physics could explain everything in the universe. The laws of Isaac Newton and James Clerk Maxwell described motion, light, and energy in a continuous and predictable way. However, by the late 1800s, some experiments began to show results that classical physics could not explain. This created a scientific crisis that led to the birth of quantum theory. The breakthrough came from German physicist Max Planck in 1900. Planck was studying a problem known as blackbody radiation, which describes how hot objects emit light and energy. Classical physics predicted that a heated object should emit infinite energy at high frequencies, a result known as the ultraviolet catastrophe. This prediction was clearly wrong, because experiments showed that energy emission decreases at high frequencies. To solve this problem, Planck made a revolutionary assumption. He proposed that energy is not emitted continuously, but in small, discrete packets called quanta. This idea meant that atoms could only emit or absorb energy in fixed amounts, not in any value. Planck introduced a new fundamental constant, now called Planck's constant, which relates the energy of a quantum to its frequency. Although Planck originally thought this was just a mathematical trick, his theory perfectly matched experimental data. Planck's idea soon inspired other scientists. In 1905, Albert Einstein used quantum theory to explain the photoelectric effect, proving that light behaves like particles called photons. Later, Niels Bohr applied quantum concepts to explain the structure of atoms, showing that electrons move in fixed energy levels. Scientists like Erwin Schrödinger, Werner Heisenberg, and Paul Dirac further developed quantum mechanics, creating a complete theory to describe the microscopic world. Quantum theory changed our understanding of nature. It showed that particles can behave like waves, energy is quantized, and uncertainty is a fundamental part of reality. These ideas were very different from classical physics and challenged traditional views of the universe. Today, quantum theory is the foundation of modern technology. It is used in semiconductors, lasers, computers, smartphones, medical imaging, and many other technologies. Without quantum theory, much of modern science and technology would not exist. Planck's constant is one of the most important numbers in all of physics. It was introduced by German physicist Max Planck in 1900 during his work on blackbody radiation, and it became a key foundation of quantum theory. This constant represents the smallest possible unit of action in nature and sets the scale for how energy behaves at the atomic and subatomic level. Planck's constant is usually written as h, and its value is approximately 626 times 10^3 joules-seconds. Although this number is extremely small, it plays a huge role in understanding how the universe works at microscopic scales. Planck discovered this constant when he proposed that energy is not continuous, but comes in discrete packets called quanta. He found that the energy of a quantum is directly related to the frequency of radiation by the equation E = h nu, where E is energy, h is Planck's constant, and nu is the frequency. The importance of Planck's constant lies in the fact that it marks the boundary between classical physics and quantum physics. In everyday life, Planck's constant is so small that quantum effects are not noticeable, and classical physics works well. However, at the atomic and subatomic level, Planck's constant becomes significant, and quantum mechanics is required to explain physical behavior. This constant determines how particles like electrons, photons, and atoms behave and interact. Planck's constant is also fundamental in many key quantum concepts. It appears in Heisenberg's uncertainty principle, which states that we cannot know both the exact position and momentum of a particle at the same time. It is also used in Schrödinger's wave equation, which describes how quantum particles move and behave. Without Planck's constant, these equations would not exist, and modern quantum mechanics would not be possible. In technology, Planck's constant has enormous practical importance. It is used in the development of semiconductors, lasers, solar cells, and many electronic devices. Modern computers, smartphones, and medical imaging technologies depend on quantum principles that rely on Planck's constant. Even GPS systems and communication technologies are influenced by quantum physics. Furthermore, Planck's constant is now used to define fundamental units of measurement. In 2019, the International System of Units (C) redefined the kilogram based on Planck's constant, showing its central role in modern science. Max Planck had a profound and lasting impact on modern science. His discoveries transformed physics, changed how scientists understand the universe, and laid the foundation for many modern technologies. Today, he is remembered as the father of quantum theory, and his work marks the beginning of modern physics. Before Planck, scientists believed that classical physics could explain all natural phenomena. The laws of Isaac Newton and James Clerk Maxwell described motion, light, and energy as continuous and predictable. However, some experiments could not be explained by classical theories. Planck solved one of these problems in 1900 by proposing that energy is emitted in small, discrete packets called quanta. This idea led to the birth of quantum theory and changed the course of science forever. Planck's work inspired many of the greatest scientists in history. Albert Einstein used Planck's quantum idea to explain the photoelectric effect, proving that light behaves like particles. Niels Bohr used quantum theory to explain atomic structure and electron energy levels. Later, scientists like Erwin Schrödinger, Werner Heisenberg, and Paul Dirac developed quantum mechanics into a complete scientific framework. Without Planck's initial discovery, these breakthroughs would not have been possible. Quantum theory revolutionized many branches of science beyond physics. In chemistry, it explained how atoms bond and how molecules form. In materials science, it helped scientists understand the properties of metals, semiconductors, and superconductors. In astronomy and cosmology, quantum physics plays a role in understanding stars, black holes, and the early universe. Planck's impact is also visible in modern technology. Quantum mechanics led to the invention of transistors, which are the building blocks of computers and smartphones. It enabled the development of lasers, solar cells, and LED lights. Medical technologies like MRI scanners and radiation therapy are based on quantum principles. Even modern communication systems and GPS technology rely on quantum physics. In addition to his scientific discoveries, Planck influenced scientific institutions and research culture. He was the president of the German Physical Society and the Kaiser Wilhelm Society, which later became the Max Planck Society, one of the world's leading research organizations. His leadership helped promote scientific research and collaboration across the world. Planck also contributed to the philosophy of science. He believed that scientific laws reflect an objective reality and that scientists must seek truth through careful observation and mathematics. His ideas influenced how scientists think about knowledge, reality, and the nature of scientific discovery. In conclusion, Max Planck's impact on modern science is enormous. His discovery of quantum theory changed physics, inspired generations of scientists, and led to countless technological advancements. From computers and smartphones to medical imaging and space science, Planck's legacy is everywhere. His work opened the door to the quantum world and shaped the scientific and technological age we live in today. Max Planck is remembered as one of the greatest scientists in history, but his personal life was filled with deep tragedies and hardships. While he transformed modern science with quantum theory, he also lived through some of the darkest periods in human history, including both World War I and World War II. His life shows that even the greatest minds are not free from suffering. Planck was a family man who valued love, discipline, and responsibility. He married Marie Merck in 1887, and they had 5 children. However, his family life was marked by repeated tragedies. In 1909, his wife Marie died after a long illness, which deeply affected him. Later, during World War I, his eldest son Karl was killed in battle. This loss was a devastating blow to Planck, who was already struggling emotionally. During World War I, Planck lived in Germany and witnessed the destruction and political chaos of Europe. Although he was a scientist and not a politician, he felt a strong sense of duty toward his country. Like many German intellectuals of the time, he initially supported Germany's war effort, but he also suffered personally as the war destroyed families, cities, and scientific collaboration across nations. The rise of the Nazi regime in the 1930s brought even greater challenges. Planck strongly believed in scientific freedom and international cooperation, but Nazi policies targeted Jewish scientists and restricted academic freedom. As president of the Kaiser Wilhelm Society, Planck tried to protect Jewish colleagues and maintain scientific integrity, but he had limited power against the regime. He chose to remain in Germany, hoping to preserve science and education during a dangerous time. The greatest tragedy of his later life came during World War II. His son Erwin Planck was involved in the German resistance against Adolf Hitler and participated in the July 20, 1944 plot to assassinate Hitler. When the plot failed, Erwin was arrested and executed by the Nazis. This loss devastated Max Planck, who had already lost several family members. He was heartbroken but remained calm and dignified, showing great personal strength. During the war, Planck's home and personal papers were destroyed by bombing, and he lost many scientific records and memories of his life. Despite these losses, he continued to support science and believed that knowledge and truth would survive political hatred and violence. Planck died in 1947, shortly after the end of World War II. By that time, he had witnessed the fall of Germany, the destruction of Europe, and the beginning of a new scientific era shaped by quantum theory. In conclusion, Max Planck's life was not only a story of scientific genius, but also of human suffering and resilience. He endured the loss of his wife, children, and home, and lived through 2 world wars and a brutal dictatorship. Yet, he never abandoned science, truth, and humanity. His personal courage and dedication make his story even more inspiring, showing that greatness can exist even in times of deep tragedy. Max Planck left a legacy that forever changed science and inspired generations of scientists around the world. He is remembered as the father of quantum theory, and his discoveries opened a new chapter in human understanding of nature. His influence extends far beyond his own lifetime and continues to shape modern research, technology, and scientific thinking. Planck's greatest legacy is the introduction of the idea that energy is quantized. Before him, scientists believed that energy could vary continuously, but Planck showed that energy is emitted in discrete packets called quanta. This simple but revolutionary idea led to the development of quantum mechanics, one of the most successful theories in science. Without Planck's work, modern physics, as we know it, would not exist. His discovery inspired many of the most famous scientists in history. Albert Einstein used Planck's quantum concept to explain the photoelectric effect, proving that light behaves like particles. Niels Bohr built on Planck's ideas to create a quantum model of the atom, explaining why atoms emit specific colors of light. Later, Erwin Schrödinger developed wave mechanics, and Werner Heisenberg introduced matrix mechanics and the uncertainty principle. These scientists, and many others, expanded Planck's initial idea into a complete theory that describes the behavior of matter and energy at the smallest scales. Planck also influenced how scientists think about nature and reality. Quantum theory challenged classical ideas of determinism and certainty, showing that probability and uncertainty are fundamental parts of the universe. This changed not only physics, but also philosophy and our understanding of knowledge itself. Planck's work encouraged scientists to question established theories and to accept that nature can behave in surprising and counterintuitive ways. Beyond theory, Planck's legacy is visible in modern technology. Quantum mechanics led to the invention of transistors, which are the basis of computers and smartphones. It enabled the development of lasers, solar panels, medical imaging devices, and many electronic technologies. Fields such as nanotechnology, quantum computing, and quantum communication are direct descendants of Planck's original discovery. His ideas power the digital world and modern scientific research. Planck's influence also lives on through scientific institutions. The Max Planck Society, named in his honor, is one of the world's leading research organizations, with dozens of institutes across Germany and collaborations worldwide. These institutes continue to push the boundaries of science in physics, chemistry, biology, and many other fields, carrying forward Planck's vision of pure scientific research. In conclusion, Max Planck's legacy is one of knowledge, inspiration, and transformation. He changed how humanity understands the universe, inspired the greatest scientists of the 20th century, and laid the foundation for modern technology. His work continues to guide scientists today, proving that a single idea can shape the future of science for generations.